Hi, everyone. Welcome to another session of the online causal inference seminar. Today, we are excited to have Oliver Dukes from Ghent University talking about non-parametric tests of treatment effect homogeneity for policymakers, and to have Edward Kennedy from Carnegie Mellon University as the discussant, and Aaron Hudson in the Q&A. Today's Q&A will be handled by Ying. So without further ado, I'll pass it to you.
Thank you, Razi. So as usual, please submit your questions through the Q&A section using the button at the bottom of the Zoom window. Please do submit it through the Q&A instead of the chat for us to better track it. So we have Aaron Hudson asking some of the questions, but I will sometimes also raise clarification questions to the speaker and also raise other questions to the speaker when they stop for questions. So without further ado, please feel free to get started.
Can you see my screen? My slides? Okay. And it should be on full screen mode.
Yes.
Yeah. Okay. Okay, great. Well, thank you so much for the kind invitation to speak today. So yeah, I'm talking on non-parametric tests of treatment effect homogeneity for policymakers. So this is joint work with Mats Stensrud at EPFL, Riccardo Brioschi, who's a master student at EPFL, and Aaron Hudson at the Fred Hutchinson Cancer Center. So a special thank you to Aaron, of course, for being in the chat today and helping with the questions. And I should say that a preprint of this work has just been added onto arXiv last week. So the reference is down there, but if you just type the name in, you should be able to find it. So I couldn't resist the chance to do some promotion for those interested in causal inference. The European Causal Inference meeting next year, 2025, is in Ghent, beautiful city of Ghent in Belgium. And we're currently, the website has just gone live. So if you look at the link, so just an encouragement for those, for people to put the date in the diary. And we'll soon be announcing invited speakers and eventually opening up for inviting submissions of abstracts. Okay. So treatment effect heterogeneity, all right? So of course, this is an aim of many studies looking at how treatment effects vary among subgroups of individuals. So this is in a way sort of a premise of the movement of personalized medicine, that there is some treatment effect variation between different individuals. I think by just looking at the previous talks in the online causal inference seminar, you'll see that this has, of course, been a big topic in methodological causal inference in recent years. And I think, I mean, there's sort of been various directions of work, but I'm sort of just to sort of like use a crude categorization. One direction of work has been on non-parametric estimation of the conditional average treatment effect, or the CATE. So a few references down here, and of course, several important ones by Edward Kennedy, the discussant. And I think the focus of this work is sort of looking at high quality estimates of the CATE, using tools from non-parametric statistics, machine learning, and sort of conceptualizing optimality in terms of rates. A second strand of work has looked rather at treatment rules or policy learning. So there's, of course, connection between these literatures, but there the focus is rather to deliver a treat or not treat type rule to practitioners. So both of these, there's been huge developments in both of these directions, and at least the area of application that I'm familiar with, which is medical research. There's been interest in actually applying these tools in the last 5 years or so in real data sets. So a kind of few references on the slide here where these methods have been tried out or at least discussed for practitioners. And here is this is a figure from the article from the bottom left-hand side, which is like a sort of tutorial paper on causal machine learning in nature methods. And here we have a possible Kate curve, where we have the age on the x-axis and the treatment effect on the y-axis. And we see that treatment seems to be less effective for younger patients and then increasingly effective for older patients. When I look at this and think, okay, this is sort of course, great for personalizing treatments in future decision making. But of course, as statisticians, we're also interested in quantifying uncertainty that comes along with our estimates. And one of the areas for future research in the article was discussion of uncertainty quantification. So, for example, point estimates might indicate substantial effect heterogeneity, especially in settings with limited data, while in fact there may be little. So the question I kind of came to this project with was, well, how can we give some measure of uncertainty quantification in these treatment effect heterogeneity type settings? And today I'm going to propose an approach through the kind of framework of hypothesis testing. All right, so before I can actually go into details, I'm going to pull back even further and think, what do we mean by effect heterogeneity? There's actually various definitions, at least in the biostatistics literature. So one definition of heterogeneity is quantitative effect heterogeneity. So meaning that treatment is more effective for some individuals than others. So for example, we have two patients on the slide. The vaccine is working fairly well for this first patient, but you can see for the second patient, it's extremely beneficial, right? So they are getting much more of a benefit than the first one. All right, so in this case, we might say that the vaccine is more effective for some subgroups than for others. Another notion that's been much discussed is qualitative effect heterogeneity, right? So this is where treatment benefits some individuals and harms others. So you see for this first person, the effect is beneficial, but the second person now, it's actually, the vaccine is harmful for them. And of course, this is the sort of qualitative heterogeneity is, of course, very relevant in policy learning, right? This is when we decide to treat some individuals and not treat other individuals, with the idea that we don't treat individuals for whom treatment might be harmful. Okay, so there's, of course, connections between quantitative and qualitative heterogeneity. So you can't have qualitative without quantitative heterogeneity, right? Because there has to be some variation in the treatment effect for it to harm some individuals and benefit others. On the other hand, quantitative heterogeneity is often dependent on the scale of choice. So it may not exist in some scales, but then will exist on others. Whereas qualitative heterogeneity is sort of independent of the scale one is working on. Okay, so when we have a small number of subgroups, it's pretty straightforward in order to construct tests of the null of no quantitative heterogeneity. For example, we could estimate treatment effects in the different subgroups. So suppose we have two subgroups of interest. Estimate treatment effects in both of these, and then we just look at whether the difference is close to zero, right? So we can basically use a simple z-test procedure to compare effects between groups. For qualitative heterogeneity, so is treatment harmful for some people and beneficial for others? There's also several tests available, with most of the focus being on discrete or binary covariates. So in particular, one may use the Gale-Simon test or the range test. And there's actually other methods available, but these methods basically tend to be the same in the case where we have two subgroups. In this case, basically, you just want to see if there's a positive effect in one subgroup, a negative effect in another subgroup, and whether after scaling the estimates by their standard error, they're sort of sufficiently far away from zero. And this is sort of, I'm just illustrating it by the rejection region of the test, where the sort of white areas indicate where we would reject. Okay, so we have pretty simple methods available to us when there's a small number of subgroups. What if there are many subgroups, and what if in particular there are infinitely many subgroups, right? So for example, in the vaccine world, we might ask, does vaccine efficacy depend on a biomarker for immunogenicity? And of course, there's sort of various sort of ad hoc approaches one could use in this type of situation, but the aim of this project was really to provide a sort of principled framework for non-parametric inference for quantitative and qualitative heterogeneity with infinitely many subgroups. So of course, infinitely many subgroups will occur if we have continuous covariates. So sort of at a high level, if you think, what am I offering today? It's, if you're sort of familiar with methods like the Gale-Simon test, I'm sort of providing an extension that works for continuous or mixed continuous and discrete covariates. So of course, we're not the first people to look at non-parametric tests for heterogeneity or tests of homogeneity. So several papers have considered tests of quantitative homogeneity. So a few references below. Other people have looked at tests, whether non-parametric tests for whether the Kate is non-negative or non-positive. So these tend to be a little bit closer to what we're going to propose today. I am going to come back to some of the similarities and distinctions with existing work, but I'm going to kind of do that later in the talk, time permitting. So I think at a sort of high level, we're just hoping to provide a unified framework, so which combines certain elements from some of these existing tests that sort of can be tailored to the type of heterogeneity one is interested in. And we're also trying to draw connections with the literature on policy learning and evaluation in this problem. So now to be a little bit more formal. So suppose we observe IID random vectors, right? So we're going to have an outcome Y, which in theory can be continuous or discrete, but maybe it's easiest to think of it as continuous for now. X is a binary treatment. I mean, A is a binary treatment, and X is a covariate, which is possibly continuous, right? But it can have many, many categories, even if it's discrete. So I'm in a sort of point treatment setting. What I'm going to propose today can work for randomized trials, but also observational studies subject to some assumptions. Y of A is going to be the counterfactual treatment with treatment fixed at a particular value, little a. So it's pretty standard from the causal inference literature in terms of the notation. So in terms of like the causal effects we're interested in, there's one effect is that the average treatment effect, which I called tau bar. And then tau of X is going to be the conditional treatment effect, where I'm conditioning on X, so the effect in different levels of X. And this is basically all of the identification in the talk, right? This is very old results, but the Kate can be identified as the difference in these conditional expectations, and the average treatment effect, tau bar, is just identified as the average of the difference in conditional means. So the talk today is really going to focus on additive quantitative heterogeneity, I should say, but extensions to other types, other scales is definitely an interesting topic for future work. All right, so quantitative heterogeneity or additive quantitative heterogeneity exists when the Kate is not equal to the average treatment effect for some values of X. And qualitative heterogeneity exists when there exist values of the covariates, where for some values the treatment effect is greater than 0, and for some individuals, some values, the treatment effect is less than 0. Right, so this is just sort of like mathematically stating what I had discussed more heuristically previously. And immediately you can see the problem we run into, right? If we if X is continuous, because we now have infinitely many subgroups in order to evaluate these hypotheses at. So in theory, it's not really a practical solution to try and estimate the the treatment effect at every single value of x, because of course, without further conditions, the variance is just going to explode. So in really what follows, I'm going to talk about, rather than looking at these hypotheses sort of over all the individual values of x, I'm rather going to try and base my inferences on a sort of a combination, right, a summary of the different subgroup effects. And that's I know that using semi-parametric theory, I can obtain well-behaved estimators of this amalgamation of the subgroup effects. So this is an example of like an omnibus test. So we're basically going to perform our test of homogeneity based on the amalgamation. All right, so this may sound a little vague, but we'll now get into the specifics. And we'll do this in the case of quantitative heterogeneity, and then I'll move into the qualitative case later in the talk. Okay, so we have three plots here. So we have the covariate x on the x-axis, the kate on the y-axis, right? And you can, and maybe for the sake of simplicity, I can assume that that the x is uniformly distributed, right? So in this first case, there's no effect homogeneity, which is just saying that the conditional average treatment effect is equal to the average treatment effect over all values of x, right? But in the second case, we do have quantitative effect heterogeneity because we see that the blue curve deviates from the red dotted line. And one way to summarize that heterogeneity would be the area under the curve, right? Above and below the curve, I should say, above and below the ATE, right? Because if there's no area under the curve or above the curve, then it means that there's no effect heterogeneity. So the sort of like the larger the effect, the larger the area above and below the curve is, the more pronounced the heterogeneity is. Right. The same idea actually is going to also work for qualitative effect heterogeneity, because now we have both regions above and below zero, right, where the red regions indicate where treatment is harmful and the yellow regions indicate where it's beneficial, right? But we're again going to sort of look at the combined area above and below the curve in order to summarize heterogeneity. Okay, so we can restate the null hypothesis of no quantitative heterogeneity as the integral of the absolute difference between the kate and the average treatment effect. So you can think about this as being like the density weighted area under the curve. Of course, when there's no heterogeneity, then the expression is going to equal zero, and larger values indicate more and more heterogeneity. So, of course, we have an absolute value in the integral. So we know that we're going to have that Q is going to be non-negative. So in fact, Q is zero under the null hypothesis, and as can be straightforwardly verified. And when there is heterogeneity, then Q will be greater than zero. Okay, so we now have a sort of like functional on which to base our test, right? This guy Q, the integrated absolute value of the difference between the kate and the ATE. But the problem is this isn't like many of the sort of nice functionals that we often work with in semi-parametric causal inference, where we could obtain an efficient influence function and then base the test on the influence function. Yeah? And the problem here is that standard non-parametric functional estimators, in this case, would have an intractable limiting distribution under the null. And this really relates to the fact that the null is at the boundary of the parameter space, right? Because Q cannot be less than zero. So in order to get around this, we're going to represent Q as a type of optimally weighted treatment effect. All right, so now I'm looking at another integral. except rather I don't have an absolute value anymore, right? But I have this weight function, little omega. Right, so little and the weights can be between -1 and +1. Right. So okay, if I back up a bit, if I think about possible different values of omega, suppose I try and maximize this expression at the top over the weights, right? If I try and choose the weights to obtain the largest possible value of this integral, right? Then the best weights I could choose would be to allocate -1 for someone whose treatment effect is less than the ATE, and allocate +1 for someone whose treatment effect is equal to is larger than the ATE. Right. So it turns out that like the maximizer of this expression would be the sign of the difference between the Kate and the average treatment effect. All right. So basically, but for any choice of weight function, right? The supremum over the class of weights is going to be upper bounded by Q, large Q, which is the previous functional we were looking at. And this inequality becomes an equality when our class of weights includes the maximizer, which is the sign of the difference between the Kate and the average treatment effect. All right, so the key idea basically is that we can, this little q omega is going to be a type of quantity that we can sort of easily do semi-parametric inference on. And then if we look at the supremum over all weights within the class, then this will be upper bounded by the quantity we're interested in. So if we find large values of this quantity, then this is going to give us evidence against the null of no quantitative heterogeneity. All right, so to detect heterogeneity, it suffices to show that this supremum over the class of weights is bounded away from 0. Okay, so why does this work? Well, for any particular weight function, this is just a weighted treatment effect, little q omega, right? So it can be easily estimated using its influence function. And you have to, and one can remember, right, that even though big Q is cannot be negative, little q omega can be positive or be negative. So we don't have issues on the boundary. So when the function class is not too complex, or the class of weights is not too complex, we can also characterize the null distribution of the supremum over the function class using empirical process theory. So the idea is that basically for any fixed weighting function, we can show that the resulting estimator based on the efficient influence function is going to be asymptotically normal. We actually have a stronger result from the empirical process theory, which says that these weighted treatment effect estimators across all the different choices of weights, these are going to converge jointly. And we can also furthermore show that the supremum over the class is also converging to a kind of Gaussian process. And this makes testing straightforward because we have ways to at least simulate from the null distribution in this case, and then we can reject the null for large values of this supremum statistic. Okay, so one thing I've been silent about so far is choosing the function class. So maybe it seems a little mysterious what this big omega is, but you can think about this as being like a class of decision rules. In fact, maybe it's easy to think of fixed rules, but it can also include stochastic rules for whether to basically predicting whether someone is above or below the average treatment effect based on their covariates. All right. So maybe you can think of a situation where you might want to treat only people whose effect is greater than the Kate on the additive scale. and that you might learn a decision rule in order to implement this. So this is kind of the situation we're in here, right? So we're sort of trying to learn like the optimal rule, the type 1 error control is preserved whether or not the class we've chosen includes the sort of true optimal rule. Basically, I just need to assume this class of weights. This function class is Donsker, and then that's sort of okay to guarantee the type 1 error. Of course, the choice of function class is going to have a potentially dramatic impact on the power of the test. And there's a delicate balance that I think is sort of an interesting aspect for future exploration, which is sort of trading off making this class too small and too large, right? Because if it's too small, it may not contain a good approximation of the optimal rule that we're interested in. And if it's too large, then our supremum statistic of which we're basing our test is going to have extremely high variance. All right, so there's sort of a delicate balance here, and we'll see a bit of that later on in the simulations. Okay, so in terms of actually making concrete suggestions, we've been able to draw on lots of interesting previous work on classification, nonparametric statistics, and policy learning. So linear decision rules or linear threshold rules are, of course, a natural class to choose from. And in the simple case where X is a scalar, which is what we're looking at in our empirical examples, then you can basically implement these by thinking about different levels at which to threshold X. So it would just be optimizing over all possible cutoffs of the covariate X. So there's also this bounded variation regression, which we'll look at in the simulations. And this is sort of similar in some aspects to it's like a non-parametric regression method with a basis expansion and penalization in terms of this penalty parameter lambda. So lambda is basically sort of relates to the total variation norm of the class. So basically, if we set lambda equal to 1, we'll have a class of monotone functions. And if we make it equal to 2, then we'll have convex or concave functions. This is very familiar from the literature on image denoising, so it's very popular there. And there's plenty of other classes one can consider based on these the literature on policy learning and inference on conditional moment inequalities. Okay, so just at a high level, how does the test work? So we first have to specify a class of functions between -1 and 1, right? And this is like relates to this decision rule predicting whether someone is above or below the average treatment effect. So we estimate nuisance parameters, which is the propensity score and the outcome regression. In fact, we only have to do this once. It doesn't depend because they don't depend on the weights, omega. And then we estimate our parameter of interest using this supremum statistic, where we take the supremum over this pre-specified function class. And we can sort of rely on lots of the beautiful work people have done on implementation in policy learning and so on to actually do this, take the supremum, because it's often turns out to be tractable in practice. To calculate the null limiting distribution of the supremum statistic, we can use the multiply bootstrap. And then we reject if the supremum statistic is greater than the 1 minus alpha quantile of the null distribution. Okay, so that's the outline for quantitative effect heterogeneity. For qualitative heterogeneity, it is closely related, but we're now going to have 2 estimans, right? 2 summaries of heterogeneity, right? One is the average treatment effect for people who have a beneficial treatment effect. So that's Q+. The other is the average treatment effect for whom the treatment is harmful, and that's Q-. And therefore, I can restate the null of no qualitative heterogeneity as basically saying that either that one of these parameters is equal to 0. Right? So, for example, we would have no qualitative heterogeneity if the average effect in those who the treatment is harmful is equal to 0, right? Because there's no one in this group. So now I'm basically going to use the same idea as before. There's a few subtle changes, right? So firstly, I'm now going to take my weight delta in the unit interval, right? And now I have the integral of the kate times by this weight function, and this weight comes from a large class. And then basically the effect for people who treatment is beneficial, this is lower bound. This is lower bounded by this supremum of little q, little delta, which is taken over this function class. And likewise, an upper bound on the effect for people who treatment is harmful is this infimum right? So basically, we can construct an estimator of the weighted treatment effect, Q delta, and then we determine whether the supremum is bounded away from 0 and the infimum for Q1 minus delta is less than 0. Right? So it's like we're doing basically 2 one-sided tests. But each of these one-sided tests is basically using the sort of similar procedure to what we did in the case of quantitative heterogeneity. I should say quickly that this is really, we were sort of using idea that previously was quite closely related to policy learning. This is very similar to the sort of objective function people have used in policy learning. And you can think of the idea that these, in terms of optimizing over delta, we're trying to basically learn the optimal treatment rule. So generally, with composite null hypothesis, like in the qualitative case, we have less power to reject the qualitative null. And this is because there's many values of the parameter are actually compatible with the null. Right, so to sort of spell this out, right? So for the quantitative case, we only needed to ensure type 1 error is controlled when the difference between the kate and the average treatment effect is equal to 0. But for the qualitative case, we need to ensure type 1 error is controlled for any value of the kate that is non-positive for all of x or non-negative for all of x. Okay, so to give you a bit of idea of why this is difficult, if you think of this plot of 2 subgroup effects, the shaded gray region indicates where one of the effects is positive and the other is negative, right? And this point, this white dot is in the middle, is basically where there's no effect in either subgroup. So if there's no effect in either subgroup, then we know that there's no heterogeneity. Right, and in fact, at this case, the rejection probability of our test is going to be extremely low. So it's actually going to be much, much lower than the alpha level, right? So we're going to be conservative, right? But if we make the effect in the people, the beneficial people, a little bit positive, and the effect in the non-beneficial, in the harmed people, a little bit negative, then our rejection probability is going to jump up, but it's only going to jump up by a little bit, right? So it still could be lower than alpha, right? So the power can often be, we can often see low power for the qualitative case. All right, so some simulation studies just to illustrate the methods. So we have 3 covariates, uniformly distributed. So a binary treatment, which is generated using this, using the model on the slide. The outcome is generated using this model here. So I haven't really said what H is, but the most important guy is this tau of x3 here. So there's only heterogeneity with respect to one covariate, which is x3. And I'm going to look at the next slide on different types of Kate models we considered. Nuisance parameters were estimated using the highly adaptive lasso. And there was 2 implementations of our tests. So one that used linear threshold rules. So this should be well powered in a case where this is powered. This is sort of like a monotone class, so should be powered when the Kate is monotone. And the second class is the total variation norm parameter, the bounded variation regression with the parameter lambda set to 2, which should be able to capture some non-monotonicity. Okay, so we considered a setting with no heterogeneity, a setting with quantitative heterogeneity, right? You see that the curve doesn't go below 0. A setting with qualitative heterogeneity, and then a setting with complicated qualitative heterogeneity. So now it's like a sine curve type structure. So when there's no heterogeneity, we see that at least in larger samples, all of the methods we consider are basically having correct type 1 error. And in fact, we see conservative behavior for all of the qualitative tests. So we also combined, well, maybe I'll say a bit more about the comparators in a minute, but all of the methods we considered basically like we're either sort of doing close to the nominal level or exhibiting very conservative behavior. So for quantitative heterogeneity, so I'm now removing the qualitative tests, but we considered our two procedures, which are in blue and in orange. And then we considered a quantitative test, which would basically just relied on a sort of arbitrary grouping, discretization of the covariate X3, right? So, and this discretization was not optimized for power in any way. So you see that the power properties of our tests tend to be better, and both of our tests implementations are doing pretty similarly. For the qualitative heterogeneity, this is a slightly more nuanced picture, right? And we compared our methods with the Gell-Simon test, where we also considered a sort of discrete categorization of the covariates, and also this range test. So in terms of the power, we see that the monotone test is doing best, and this makes sense because it's sort of we've chosen the right function class in that case. But the non-monotone test, its power is slightly lower, and this reflects the fact that maybe we've chosen a more complicated class than is necessary, but the power is still pretty decent. And both of these methods are still outperforming the Gell-Simon and the range test. Now, when we have this like complicated non-monotone Kate, then we see that the non-monotone test is still doing very well. Actually, the qualitative test is performing pretty dismally in terms of power. And this is, of course, because our function class is misspecified. So our type 1 error is guaranteed, but not our power necessarily upon misspecification. So I should say that actually I've excluded the quantitative tests from these last two plots, but their power was doing much better than any of these qualitative tests. And this is just something that I think is more intrinsic to qualitative heterogeneity tests. Okay, so a data example. So this is a study comparing a randomized trial, in fact, comparing two treatments for HIV. We used a composite outcome, including occurrence of a 50% decline in CD4 cell count, development of AIDS or death. And we assessed heterogeneity using 3 of the covariates that were collected in the study. So in theory, we could have also done this together, but we did separate tests for each of the covariates as well. So these are the results. So you can find the p-values for each of the tests in the top right-hand side of each of the figures. So you can see that there was only a significant result at the 5% level for weight. So there's sort of only weak evidence of effect heterogeneity, of quantitative effect heterogeneity for weight. And the qualitative p-values are all very large, which sort of, again, confirms what we know, that these tests are typically very low powered. In order to give some visualization, the curves and the intervals come from a parametric regression model, and you sort of and I should say that in terms of the implementation, we went with our test based on the linear thresholding rule, so it should be good when the sort of Kate has a monotone behavior. Okay, so there's a couple of points to discuss, but I think I'm going to be brief just to give Edward more time. So the first point, I think, is that we've shown the paper that we have both type 1 error control and rate at optimal local asymptotic power. But because we're adopting an omnibus test, we in fact only have non-trivial power in finitely many directions. So basically, another way to think about this is that suppose we have a Kate which is equal to 0 for most of the population, and just for a small subgroup deviates. Then because our test is sort of based on integrating with respect to x, we may in fact have very poor chance of actually detecting heterogeneity, even though it's there in the data. And so-called smoothness tests, they tend not to be have fast power in the directions we have it, but they have power more equally spread in different directions. So one might ask, when do our tests have power? And if we think about a rule that assigns treatment with probability f, then for the qualitative tests, so is treatment harmful for some people and beneficial for others, we basically have power if there's a decision rule in our class where if we sort of implemented that rule, it would be significantly different from the maximum of the two static rules, so the treat everyone or the treat no one rules. So there's a similar sort of heuristic in terms of the quantitative test, which we discuss more in the paper. But basically, we have power when there's a dynamic rule in our class leads to different population impact than a covariate free rule. So I think maybe our tests are less designed to answer questions of existence of heterogeneity, but rather, if we would use heterogeneity as the basis of a policy, which we would then implement in a population, these are the kind of alternatives that we may be able to pick up and which may often be relevant. So maybe I'm going to skip over the next bit and just say, we've proposed tests that assess heterogeneity by estimating a area above or below the Kate curve. We have rate optimal estimators, and you can think of this as like an infinite dimensional extension of certain classical tests. So closely connected with inference on optimal treatment rules. And we have some nice properties I've not said too much about, but you can find out more about in the paper. So maybe with that, I'll stop for the moment. Thank you for listening. Look forward to hear what Edward has to say.
Thank you, Oliver, for the great talk. I think Aaron did a fantastic job in answering all the questions. So for now, we will proceed to Edward's discussion, and we can address more questions from the audience at the end, probably.
Great. Yeah, thanks a lot, Oliver. It's really interesting work, really nice talk. So yeah, just to kind of give my very short perspective, I think if you could isolate the kind of main statistical challenges here, it's that we've got these two kinds of parameters that come up in these two kinds of heterogeneity. They're both non-smooth, like Oliver talked about, so they involve these indicators, which presents challenges. And then these special null values, which we want to test, are at the boundary. And so you have these kind of weird vanishing influence function issues that come up. And so, yeah, just very briefly, right, the proposal is to switch to some kind of easier to estimate functional, which looks like the supremum over some Donsker class. And then you can get these nice results like asymptotic linearity holding uniformly over the class and things. And so, yeah, first, before any discussion, it's a really nice paper. I really enjoyed reading it. I could talk for the whole 10 minutes about what I liked about it. Heterogeneity is super important. It's a crucial part of causal inference. It's a problem that's in study a lot, but there's still lots to learn. The paper itself was just really nicely written, super clear. Yeah, these authors are people that whenever I see they have a new paper out, I always make sure and read it, just because it's fun. I really like how their procedure is both interesting, it's a neat approach to take, but it's also pretty user-friendly. And I think it strikes a nice balance between, like, you have some methods out there which are very complex, but maybe they come with nice guarantees. You might have other methods which are super easy to implement, but they're very fragile, not robust. And I think this strikes a really nice balance between these two ends of the spectrum. So yeah, just a really, really great piece of work. So I really just have two minor specific questions, and then the rest of the discussion is more about like future work. And I thought it could be a fun chance to just talk about, things that this kind of paper could spur on and future work. So the first thing I think Oliver actually already answered, which is it wasn't obvious to me reading the paper that we're really avoiding this vanishing influence function issue, but I think Oliver pointed out that the parameter space now is no longer 0 to something, and so this is maybe avoided that way, but maybe he can say more about it. I think in general, more discussion of this could be interesting, just because this kind of problem comes up a lot, especially in these testing settings where there's a special value and it's often at the boundary. And I don't know of a good solution to this problem. I think generally what people do is either kind of change the target or essentially kind of add noise. And in some sense, the fact that the influence function vanishes is good. It means you could potentially get faster rates. And I haven't really seen people exploit that, maybe with one exception, which is this paper by Luca and Vanderland and Krone from a few years ago. And they're interested in, so I think it could be nice to compare it to this paper, and I'd be curious to hear what Oliver and Aaron think about this approach and how it relates to what they're doing. So very briefly, what they do is they're using this maximum mean discrepancy functional to test hypotheses like the ones that I think Oliver and co are thinking about here. And they also have this influence function vanishing under the null issue. And so you can kind of think of, because they're going after this maximum mean discrepancy, they're also doing some kind of relaxation, not going after something like an L1 norm or something. But yeah, they still have this boundary problem, but it turns out that in their setting, the second order influence function exists. And so they actually, figure out there's some U statistic estimator, and they could show that this thing converges to some distribution after scaling by n instead of root n. So they're somehow like exploiting these faster rates that you can get. But yeah, I think this would be interesting to compare to and see how the approaches differ. So those are really my two very minor points. Yeah, it's just a really nice paper. And then it kind of spurred me thinking about some other issues, which I thought could be fun to just talk about for a few minutes. One is optimality. Another is kind of going beyond means and thinking about heterogeneity on like a distributional level. And then the third part is moving towards estimation beyond testing. So I'll just talk very briefly about all these. So yeah, in this testing literature, I think it's very common to like prioritize validity or type 1 error, and then kind of, say something like, the choice of the function class, or, some aspect of our test will influence power, but then not really explore it so much. I think this paper is not doing that. It's an exception. It gives like a nice discussion of these, like Oliver talked about, power against local alternatives. But I think you don't always see this. I appreciate this in this paper. I think you could go even farther and think more about optimality. And so this is maybe just a pitch that I think optimality and minimax optimality is really underexplored in causal. I think there are just lots of things left to learn, like very fundamental basic problems that we don't have a great understanding of in the setting. And in particular, I haven't seen really any work on like minimax testing and causal inference. So I thought I'd just talk for a minute about this. There's this nice minimax testing framework from the 80s by Inkster and colleagues. And so the way this is set up is you've got some set of null distributions. So this could be things like, distributions where the K equals the average treatment effect, for example. And then you have some set of alternatives which are separated from the null distributions in some distance by some amount epsilon. And then for any separation epsilon, you can think about the minimax risk. So this is just like the type 1 error and type 2 error for the set of null distributions and this set of alternatives. And then you want to try to find the test that makes this as small as possible, right? So it's the best possible test in the sense of this worst case risk. And then in the testing world, it's often common to think about this minimax separation or critical radius, which just says what's the smallest epsilon I could tolerate and still give you some guarantee on the risk here. And so yeah, just like a quick example that Inkster studied in the 80s is something like testing like whether a regression function is 0. And so you can think of this as being roughly similar in some ways to this heterogeneity testing problem where you might want to test whether a difference in regressions is equal to its average or something. And here in a lot of this work, people are thinking about kind of classic non-parametric models like smooth distributions where you have some number of bounded derivatives. In this case, you could think about like L2 separated alternatives. So alternative distributions where the regression function is more than epsilon away in this L2 norm. And so in this problem, the minimax story is well understood, and this minimax separation looks like the following. So it's n to the minus 2s over 4s plus d. And so there are a couple of things you get from this. One thing you get is a nice benchmark, right? You can, if you have a test, you can compare it to this optimal risk and see if you've sort of made most efficient use of your data or not, or if you need to go searching for a better, more clever test. It also, it tells you something about the fundamental difficulty of this problem, and it, like in this case, this rate is faster than the rate for estimating the regression function, which is a way of like quantifying how testing is an easier statistical problem than estimation, which is interesting. And so an open question is, what's the analog of this story for the Kate? And this has not been answered yet. So, in some sense, a very basic problem, but we don't know what happens. So I think, yeah, this is another example of where for these optimality problems, we just don't know very much yet in causal inference. Okay, so yeah, just in the last couple of minutes, right, in this paper, they were thinking about heterogeneity in terms of this Kate, which is a very natural starting point. It's sort of the most crucial, probably, piece of the heterogeneity story. But you could imagine that there are lots of other ways that treatments could have impacts on outcomes, and it could be interesting to think about, more general forms of quantifying heterogeneity, which basically involve like comparing distributions of potential outcomes, for example, conditionally on the covariates. So I've done some work with a few people in estimating counterfactual densities, which is an interesting problem. But everything we've done has been marginal, so not conditional on covariates. We did some L1 norm stuff, which you could imagine could come up in testing problems, but I think there's a lot of ways you could extend this and think about it more along the lines of heterogeneity instead of as a summary of like the distribution or the effect on the distribution. There's a nice paper by Matej Nekov and Siva Balakrishnan and Larry Wasserman from the last couple of years where they thought about minimax optimal conditional independence testing, which is also a very related problem, right? It's one example of sort of going beyond the means and thinking about whether treatment has any effect on outcomes at all within levels of the covariates. So it's kind of like a sharp null kind of thing that we had seen in causal inference. And this paper is a great example of this, minimax approach to testing. So they think about a particular set of alternatives separated in TV distance, and they've got some really nice results, showing what the optimal rates are and what kind of minimax separation you get. And it sort of looks like rates that you get in goodness of fit testing. If things are discrete, if things are continuous, you pay some penalty for like how non-smooth they are, essentially. But yeah, it's a very nice paper and has direct applications to causal inference, but it's not really framed in a causal way at all. Okay, and then the last thing I wanted to mention was just, often testing, of course, is crucial. It's a really important part of the this whole process of thinking about heterogeneity, but often we want to go beyond this, 1-0 decision of whether we reject or fail to reject, and instead try to estimate something. And so I thought I'd just tell everyone about some work I did with Matteo Bonvini, who's at Rutgers, and Luke Keel, where we tried to estimate the subgroup of subjects who actually benefit from treatment or have treatment effects larger than some theta. And there's some interesting stuff that happens. So yeah, we thought about generic plugin estimators. I think there's a lot of other avenues for different kinds of estimators you could think about. And we characterized the minimax risk. This is basically looking at like where you got the set wrong and then how far away the Kate was from, say, 0. So it's weighted, some weighted notion of risk. And we thought about, again, these kind of smooth non-parametric models where we just assume that the nuisances have like bounded derivatives. And we use this margin condition that controls how much of the mass is around the specific point you want to think about. And then we figure out minimax rates for this problem. And they're very interesting. They're kind of a mix of 3 different kinds of rates that you see in the literature. So if you look at this rate without this numerator piece, it's like a mix of a non-parametric regression rate and a functional estimation rate, like a parameter estimation kind of problem. And this is actually the optimal rate for estimating the conditional treatment effect. Yeah, this exponent is sort of characterizing the sort of extra benefit you get from this fact that you don't care about estimating the Kate everywhere. You really just estimate the Kate at this threshold. You want to see who has a positive Kate, for example. And so this is showing how this problem is easier depending on how much of this margin condition holds or not. But yeah, this is just maybe one example of a way of moving on to estimation from the testing setting. But I think there are lots of other avenues there that could be interesting to think about in connections with this work. So I'll stop there and just say thanks again for really nice work, really nice talk. I think there's a lot of cool stuff left to work on here.
Thanks, Edward, for your discussions. I would give a minute to Oliver and Aaron to say a few words.
Okay, so thank you firstly very much for the great discussion. I agree. I mean, there's definitely tons of interesting open problems to work on, and maybe I won't say much more about that. I think in terms of the comparison with existing approaches, this is definitely not the only way to handle this boundary null problem. In fact, I had a slide on this, but didn't get time to it. So even in these kind of like sort of looking at if the Kate is all non-negative or non-positive, there's other tests that have been proposed which sort of have more a flavor of a plug-in type test where you might estimate a treatment rule in part of the sample and then develop a test based on like the value function in a second split. And of course, there you have the disadvantage of splitting, right? But maybe if it's not clear to me if there's like a general story about whether one is better than the other. It's probably case dependent. We are sort of restricting more to these weight functions being in a Donsker class. The other test is more flexible, but of course you lose something through splitting. I think even if you look at sort of boundary null problems in much greater generality, so also looking at the variance of the Kate or other types of ways of summarizing, there's even more open questions, like there's different ways of doing splitting. Some ways seem to be better than others. And yeah, I mean, these all seem like functional estimation problems in some sense, but we really have a good understanding now of optimality, I think, or some understanding. But these, like in terms of testing, it doesn't seem like there's a kind of Neyman Pearson type result we can appeal to here, at least as far as I know. I mean, often we can get parametric rates against local alternatives, but maybe many different tests get these rates, and it's saying much beyond that currently to me seems open. A lot more to be said, at least. Maybe I'll give Aaron a chance to say something.
Yeah, so again, thanks for the discussion. I thought it was really helpful. And I agree with Oliver. I think my question, I guess to you and just more broadly, is I would wonder how existing minimax theory on testing relates to parametric Neyman Pearson results. And I wonder if there's sort of connection between those two and our work and Marco's work and all these other existing approaches that are based on sort of root-n, supremum, Gaussian sort of inference on function value quantities. I think second comment is relation specifically with Marco's work or Marco and Alex's work, where they were looking at this maximum MMD. is my hunch in general is that these two approaches are closely related, or you can really think about a generalization that would apply to both, where you're thinking about basically taking a projection of some function valued estimand, so a conditional treatment effect on which you don't assume any structural assumptions, and project that quantity down onto a Donsker class, or every function contained within a Donsker class. And then you perform inference based on some summary of all of those projections. So you can, for instance, the MMD, you can characterize that as a projection onto a reproducing kernel Hilbert space, basically. And in our case, we're projecting our function or the conditional treatment effect onto total variation norm bounded space, same difference. And in either case, root-n inference ends up being possible because we're basically leveraging that we're projecting onto a class where uniform inference is possible. And so we can get inference using all these sort of uniform weak convergence results in standard empirical process theory. I think that where we would start getting into trouble is where we didn't necessarily make structural assumption, or sorry, or rather where we started trying to maybe project onto a class that didn't have the Donsker property. In that case, you might need to sort of rely on some sample splitting or something like that.
Thank you so much again for the great talk and great discussion. Before we wrap up, there is another new question in our Q&A. So maybe the speakers can take a little bit of time to answer it. So the question is, in terms of holder smoothness, would it matter if you have isotropic or anisotropic situations, like in works of Veronika Rokova? Would both fit this non-parametric testing approach?
Yeah, you can always, so this means you have like different amounts of smoothness in different directions. And in this case, yeah, there's some combination of the smoothnesses that make sense in the rates, but they look kind of similar.
Great. Thank you so much.
Okay, wonderful. Thank you so much, Oliver, for your great talk, and Edward for your discussions, and Aaron for your input and being on top of the Q&A. So for next week, we are excited to have Alexis Bello from Google DeepMind talking to us about partial transportability for domain generalization. Hope to see you all next week.